Depending on your time zone, good morning, good afternoon, good evening. I'd like to welcome everyone to the Computational Storage, Your Strategic IT Advantage webinar. This webinar is presented by AIC, AMD, and NGD Systems. My name is Joe Kimpler from AIC's Office of the CTO, and I'll be your moderator today. Before we start in the classroom, let me provide a couple of quick start tips. The webinar is broken down into 3 presentations. AIC, AMD, and NGD Systems. If you'd like to ask questions, please type them into the questions box, and there'll be answers during the Q&A section of the presentations. Lastly, all presentations will be available for download from the handout section of the GoToWebinar. Today, we're going to have 3 high-powered presenters. The first is Scott Shadley. He's a VP of Marketing for NGD Systems. He'll provide a computational storage primer and a real-life demonstration of its advantages. Next is AIC's own Federico Papanini, and he will describe AIC's FB128-AG server storage architecture and how it's critical to storage computational's demonstration performance. Last, we have AMD's Greg Gibby, and he will highlight the advantages of AMD's EPYC 7000 series processors. Here's NGD Systems' presentation on computational storage. Scott, take it away.
My name's Scott Shadley. I'm here in the offices of NGD Systems. Happy to be part of this activity and kind of give you guys the introduction and primer to what's going on with computational storage solutions and how the 3 parties involved in today's webinar are participating together in some great activities. So when we start talking about computational storage, we kind of have to do a quick history and then where it is, where it's going, and how we're going to get there. So our traditional architectures today are related to architectures that have the traditional CPU, which we're going to hear more about from the EPYC 7000 system, a memory platform of some sort, and then storage, which is what's near and dear to my heart. What we've seen as this von Neumann architecture continues to evolve is that we start to run into certain pain points for architects that are using these technologies. So whether you're talking about edge platforms with physical space, hence the idea of having this fancy new FB128-AG platform, the power constraints that exist in those things. So we need to make sure that we're optimizing those types of situations. And then of course, there's things like a scaling mismatch and what I like to call the bottleneck shuffle. Where do we put the traffic jam in this architectural setup? There's ways to do all kinds of interesting things around composing, re-architecting, hyper-converging, but at the end of the day, we need to look at it if it doesn't require a wholesale change to this architecture. So if we look at the current implementation that we have in what we classify as traditional von Neumann architecture, illustrated on the bottom right, you have a very fancy EPYC 7000 processor in this amazing dual socket system from AIC, and a whole bunch of storage devices, including the ones that we're going to illustrate to you today, that create a great platform of just over a quarter of a petabyte of storage, and a lot of processing power that comes from those EPYC platforms. But there's an opportunity to look at this with a slightly different venue and direction, and add even more capability to an amazing platform that exists today in the way of this particular system. And that's where computational storage comes into play. What computational storage does is allow us to add additional scaling, add this capability of a resource offload, and in our particular instance, in the way that we're designing the architecture, a way to make it very seamless for people to deploy. So we call it a server in a server. So as you look here, basically we're adding the capabilities of CPU resources directly into a storage device. This is the ability for now a storage device which historically holds information and moves information to actually do work on that information. So in today's environment, we're collecting petabytes of data that we're interested in gathering, but we really only want the gigabyte or even the terabyte of useful information that comes from that petabyte of stored information. And moving that information back and forth and around in these architectures becomes more challenging when we get to petabyte scale. And so this capability of doing distributed processing, providing faster results, conserving power, and keeping it in these smaller 1U style footprints is very paramount to the success of these types of architectures. Now, you may ask, what does that mean from an architectural point of view, and why haven't I heard of it before? What's going on? I'll use our friends at Gartner. We received acknowledgement of this technology from them is of what we classify as the hype cycle. So as you can see, there's different levels of capabilities within this particular hype cycle, and computational storage has now entered 2 unique hype cycles, which is also something unique for architectures in this space, because you'll see that there's very little overlap of any other technologies within these two particular things. So we are adding value to the storage and data protection technologies, and we're adding value to the compute infrastructure by this combined architecture of CPU capabilities inside of a storage device. And you can see here the quote from our friends Jeff Vogel and Julia Palmer at Gartner as they talk to the value that we bring with adding this technology to the marketplace. So there's lots of opportunity and unique ways to use this architecture. What we've done uniquely in our particular case is we created what's known now in the industry as a computational storage drive. So we've participated in an industry standard body group called SNIA that works on creating architectures for storage protocols and networking infrastructure. And they defined a computational storage drive as a solid state drive, in our case, a very high capacity solution, and I'll illustrate that in a few. And it offers this capability of an applications processor in the case of, as I show here, what we call in situ processing. And this in situ processing allows you to run some very unique or very versatile applications on that stored data. And you can see here we have a single device called a CSD controller. We have your memory cache, which exists in all SSDs, and then we have a large array of NAND media. So for those that are wondering, well, how do I use it? It is an off-the-shelf, plug-and-play solid-state drive. It looks and feels just like any other solid-state drive would. However, we've implemented the ability to add that applications processor embedded into our single-chip ASIC design. Now, computational storage is a new term. It was brought to market through the SNIA organization in 2018, post the Flash Memory Summit events and the storage developer conferences, but it's not something that's brand new to the market. So what's unique is it's been around for some time, and this is an article that was recently published in the ACM Transactions on Storage that talks to a bunch of different research projects that have been available. And we can provide a link to this after the event if you'd like to contact me. It is behind a paywall, so I can give you access if you reach out directly. And what's highlighted on the top left is historical aspects of what people have done to try to address computational storage and the resources we want to bring to bear. And on the right shows a graphic of some of the implementations that exist today in the marketplace. And these graphics come from a SNIA presentation that show the different implementations of computational storage. What's highlighted in the bar behind them is the cost to entry. So if you look at, for example, an FPGA as a controller, there's a cost to the FPGA that's significantly higher than that of a controller. If you look at a accelerator in front of an SSD, it's even more costly because you're adding additional components to the basic design of this architecture. And so what we've done from an NGD point of view is we've said, let's keep it simple, let's make it low cost, to remove the barrier to entry, and create what we classify as a new version of the KISS principle. Keep it simple and seamless. So this, for us, is a very unique opportunity to engage with our partners at AMD and AIC, and the fact that we produce this in your traditional SSD form factor. So you can see here at the top, the M.2 form factor, which is very popular in a lot of new recent data center scale-out architectures, and very popular in the edge deployment marketplace. You have your traditional U.2 architecture, which is that 2.5-inch drive form factor. And then, of course, you bring in the new EDSFF E1 short, which is what the highlight of this particular webinar is about, around the innovation that's brought to bear by AIC in the FB 128AG. And from our device perspective, we took a unique approach that we said, these devices need to hold as much information as they possibly can in the smallest footprint with the least amount of necessary power. So we provide the highest capacity solution, we provide the best energy efficiency, and we provide unique opportunities to drive new form factors forward in the way of things like the EDSFF, as well as keeping track of all of the current architectures. So if you need a very dense system in the way of the FB128, current products today in this EDSFF form factor are averaging about 4 terabytes per device from different vendors. We offer 12 terabytes. So again, the scale order of capacity. Our power consumption, even with the compute resources, the higher capacity and the density, our overall power draw per device is still lower than the marketplace. So the EDSFF E1 short form factor allows 25 watts per drive. We don't need that level of power, so we bring that energy efficiency back, allow for better scale out in data centers where there are power constraints, because we all know in today's environments, power is actually one of the most important parts of a data center design right now when we're trying to get into these green and zero impact and carbon neutral type platforms. So if I take another look at the computational storage view of that same platform I showed you previously, You went from 288 terabytes of storage to half a petabyte, 432 terabytes of storage. This is amazing, wonderful, extra great addition to the platform. But what's really unique is we've added 144 additional CPU processing cores. Now keep in mind, that EPYC processor is needed to do a lot of great work, but we can augment and supplement that with this computational storage solution by giving you these 144 additional cores to do localized search, sort, data management of the individual devices' stored data. That's a very unique thing that hasn't been really pushed forward today and is what the purpose of computational storage is. And in this particular platform, if I look at it as a 1U going into a rack, I now have 42 times that capability in a system versus the traditional architectures of some of the 2Us and other platforms. And if we move to the edge, we see even greater value. So how do we do all of this? The next question is, okay, you've got an SSD, you've called this great thing called computational storage, we're gonna have some fun with it, but what did we actually put in the system? So if you look at it from a very marketing friendly, because I am that marketing guy, we have a traditional NVMe SSD, you have the NVMe interface sitting right here that's talking between the host platform and the SSD itself, and we've built a new bridge, and that new bridge comes into this ARM platform. This ARM platform is an applications processing core that literally allows us to put a Linux OS or other OS into the device itself, and that now allows us to run applications and manage information being stored in the SSD without the host actually moving any data out. So we bring the data in, we store it, we do work on it, and we can return the results to the user. All of this being done over a seamless NVMe protocol interface. So we've reinvented the SSD architecture by adding the capability to do truly meaningful work. So we've heard things like intelligent storage before, and historically intelligent storage meant I'm doing a good job of protecting it. I have ECC, I'm doing this where leveling and moving data around so that it doesn't get lost in translation. But this is doing actual real data work on the drive. And so what does that look like? Well, we've had the opportunity because of this Linux OS platform to be engaged in a plethora of opportunities with our customer base. So we're talking edge platforms, for example, and that picture there is showing what's classified as a small sat. We recently won an award with the US Space Force to be one of the first storage devices into space. On the autonomous anything side, engagements with autonomous manufacturers is very key because there's a very power budget centric aspect there. And so some of the embedded systems that are available are taken advantage of in that case. Your traditional data center and CDN platforms, we've all started streaming more. It's a great opportunity to do more intelligent work with that data that you're managing, both metadata of users as well as deployment of the actual media. And of course, this concept of smart everything, the IoT implementations, the smart homes, all of these utilize many of these different workloads that you see on the screen, from things like VMware Tanzu to AWS Greengrass to MongoDB, and including AI and ML workloads like PyTorch and TensorFlow. And what we're going to do is spend a few minutes going through a couple of demonstrations of several of these particular use cases so that you can see what's really happening with this workload. Again, I need to make it easy for you to understand so that you know how easy it is to use so that we can start doing deployments of this technology that benefit the market, you as our customers, and your customers as your customers. So the first demonstration I want to talk to is a very edge-centric demonstration. And this is talking about a single device being used to actually communicate with the Azure IoT Hub and Azure environment. So we all know that we're going to cloud-based platforms and we're doing a lot of local storage, i.e. the FB128, and we're doing a lot of cloud storage. And when we do cloud storage, we want to interact with the cloud. One of the unique things about cloud environments is there's no tax for putting data into the cloud. There's a massive tax for taking data out of the cloud. And that's where they make a lot of their value-added efforts. So our ability to limit the amount of data going back and forth and saving you on both cost and time is very paramount to this work. So what you see here is a screen capture of our what is about to be a video I'm going to show you. On this left side, this is the host Linux OS. And on the right side, you'll see is the drive level Linux OS. Now, it's so easy to use that we actually have a command line into each and every one of our devices. And so as we go through the video, you'll see work being done on the device versus work being done on the host, and how much of the offload of that compute resource can actually be done through this processing. So let me go ahead and turn off my laser pointer, click on our video, and so what I'm going to do is I'm going to jump through. This video is available online, But what we have here is, this is the Azure IoT Hub being accessed by the host device. We're creating this edge infrastructure that we need to have available. Now, traditionally, this particular IT hub engagement where we have an edge agent and hub, those will be hosted on the OS and the CPU on the device, not on the device, but on the host system. So what we're going to do here is, you can see here's the host, here's the device. As we go forward in this development of this platform, we're going to start actually interacting on the device side. So all this work, this is one of my engineers doing this demo as a recorded fashion. He's interacting command line level with the OS on our storage device. He's not using the host. The host is there to capture data and to be a pass-through of the networking protocol at this point. So here he's kicking off the particular IoT platform. If I jump forward a little bit so we can have some fun with some other demos, you can see we're creating a computer vision application on Azure where we're going to utilize a service on Azure, but not actually move data back and forth to Azure. So we're actually able to use an AI algorithm that they supply. And you can see here that we have an image analyzer up and running on an edge client. So now I'm going to use a Docker platform to be able to encapsulate that. And I'm going to kick that application off. And it's going to sit there and start running in the background, waiting for data to show. So now I've done all this work. You can see as I've jumped through the video for quite a bit, nothing's been done on the host interface. Now I'm going to go back and actually use the host. I'm going to go out and grab a picture from the internet of the Leaning Tower of Pisa, even with the background and all that fun stuff. And for the first time in this whole demo, which runs about 8 minutes, I'm now starting to interact with the actual host platform. All I'm doing is getting the image from the internet, storing it to the storage device. Now, as the storage device is sitting here with the application running in the localized OS, it's waiting for something to show up for it to process. Within instant time of that image being moved into the storage location, it's gone out, done all the work, and it's identified this product as a Leaning Tower of Pisa. So 100% offload of all of the processing of the data for this particular example is being done in a command line level of the device itself. So that shows an example of how computational storage can be deployed real world with a cloud complemented infrastructure. So there's also other ways to look at this architecture. So we have another version, and again, a link is in the handouts, to e-discovery. So one of the biggest things about e-discovery, and it's come into play a lot with things like doing ancestry type research or doing document loads of information that you want to be able to search, is you get PDFs, you get JPEGs, you get documents, you get PowerPoint slides. You need to be able to search all of that. And a generic search engine works best when you have something that can do OCR, or optical character recognition, of a text file. And we worked with a partner company called Data Storage Science to implement an AIC FB128 implemented solution that uses an M.2 in a carrier to do an OCR application of this. So again, no new hardware, no new software. Everything's being done with traditional storage plugged into traditional servers, but adding value through computational storage. So I'll let you go ahead and take a look at that after we're done with the presentation via the link that exists here, or going to ngdsystems.com. Now, I do have one other great example of machine learning actively running on the device itself. We're doing this with our partner ARMs. We do use the ARM cores, and just to highlight the value of the partnership there, ARM is also highlighting that they agree that our architecture works very well in the infrastructures of today. So here's a great quote from one of their principal storage architects. He's also the co-chair of the standards body group that's driving this as an architecture moving forward. So great support of this, both from a partner, an enabler, and a partner in the work to do things in the way of standardization of this technology. So lots of opportunities exist. So I have a demo here that I want to highlight, and this is getting close to the last of what we're going to show. This is the ARM neural network framework, and you can see there's a bunch of information blocks that are utilized for this. What we're doing is we're carving out the only ones necessary to actually run a neural network on our devices by removing the need for a GPU, a neural processing unit, or a driver, and some third-party software. Everything's going to run locally inside our device that's within this black outline. Now we've got 100,000 plus images per device that's plugged into this particular FB128 system. And this was recorded on that exact platform that we've been talking about today. The output is shown in two different ways. So if you look here as I run this demo, the CPU is running the image analyzation tool. As soon as we activate one of our devices down here, you can see the host CPU is now free to go do anything it needs to do outside of simply identifying a picture. What you see here on the top left is one of the devices actually identifying every image as it's open. Now, Down on this particular window, we're adding devices. So the server holds 36 devices. We loaded 18 of them in this particular platform. The images are starting to come up more frequently because we're processing them more efficiently. Each device is processing its own local database of images real time. Again, the host is sitting basically idle. All this work is just simply to open the pictures. What the problem with this particular platform is, as we open these number of devices, the images are being analyzed so fast by the individual product, we can't actually pop the images to the screen in the 150 milliseconds it needs to actually be visible on the screen. So it looks like we're not working. What we're doing is we're working so fast you can't actually see the work being done. So in order to better see that work being done in parallel, we're going to look at it this way as a text output. So I have one drive active, and you can see that same drive over here, again, is showing the 1 and 1. The CPU, again, goes from running at 100% to almost 0. Now I've added 2 drives. Notice the number of images being processed doubled. I add the 3rd drive. I'm now processing 3 images at a time, not just 1, but 3 at a time. Let's drive in drive number 4. All of a sudden, you're processing 4 images at a time. So again, the CPU can do a lot of great work, but let the CPU go do things that are paramount to utilizing this data. So that the CPU doesn't need to identify these images. It needs to know what to do with the identified images. And so while that CPU is off running other applications, I continue to add devices. We're up to 6. And you can see the number of drives processing images are basically replicating this top. Each drive is processing just this fast. So this is a real-time offload of computational storage running a neural network, doing image recognition for this particular case. It could be live video, it could be object tracking, it could be any kind of data set, it could be a search algorithm like Elasticsearch, it could be database information that you're looking for. The idea here is this is a live example of how quickly parallel distributed processing with computational storage drives brings significant value to already existing great architectures. So what I'm going to do is leave you with FP128AG storage server built on computational storage. So again, 12 drives times 36 is 432 terabytes of raw storage, 144 processing cores. So if I were to put all 36 drives in that particular system, you would be able to get 36 parallel processing engines, all with 4 cores apiece. So I'm giving you more than 50% more storage by utilizing an NGD EDSFF at 12 terabytes compared to the competitive landmark. And because I'm consuming less power and I'm letting the CPU be used for other tools, I'm giving you better than 20% overall power reduction in the overall platform. So EDSFF is great. Being able to drive density is important, but being able to drop power per device and allow the system to be used for other tools and letting that CPU power be used for other benefits is a significant value that this type of platform will bring to the market as computational storage servers are started to be rolled out. And you can see down here on the bottom right picture, that's actually my partner in crime, Federico, who's loading the server in our labs as we were working on that together in the last quarter or two to get these products up and running. So I thought it'd be fun to show that how real time we're doing this and working together from that perspective. So with that, I'm going to say, how can we help? We're going to have a great virtual happy hour. I look forward to lots of questions and an opportunity to engage the audience as we move forward. So I'll go ahead and hand it back over and we'll continue the presentation.
Welcome to today's webinar. My name is Federico Papayani. I am one of the PM here at AIC. For the last 10 years, I dedicated myself on studying storage and storage architecture. Today, I'm presenting a new storage server, the FB128AG. I'd like to start with a problem statement that every storage architecture faces in modern times. First and most, either system have high capacity or high speed. And having both ramping up is actually very difficult and in most cases very expensive in initial cost and also in rack queue. So the other issues is generally on the resources the computer can assign. Generally, they're focused either on the media storage or on the IOs. Third is actually the latency. More the system grows, more the latency accumulate. And in modern times, latency means unusable data. At last, not all the workload are the same. file size, file length, way to read the file is all different. So no two data pools are the same, no two workflow produces the same data. So let's see how we at the AIC look at the problem and we try to fix it. At the core of any computing and storage platform, there is always a processor. AIP Chrome was the clear winner in this race, providing not only more cores, but also more PCIe lanes, and all PCIe Gen 4. Also, with the better wattage, we can design a better thermal solution with a less power consumption. To maximize the potential of the AMD EPYC CPUs, we designed a motherboard where all 128 lanes are balanced between the front of the unit on the media to the back where the network I/O resides. Doing this allows us to have iron out any possible bottleneck from the data flow. Here's the complete design, the Ariga motherboard. As you can see, the I/O in the back is pretty dense, the highest in our new form factor. We have two PCIe Express x16 PCIe Gen 4 and OZP mezzanine. Going to the front, we have 64 lanes in slimline form factor, which allow a really high amount of NVMe drives. So a perfect ecosystem, front to back PCIe Gen 4. Now let's take a look at the old system. At the AIC, we found a way to install two of those motherboards in our new system. The operating system is generally residing in one of the M.2 on the motherboard, which allows us to have a full storage in the front, up to 36 E1S drive NVMe PCIe Gen 4. Looking at all this data, it will be pretty much a waste not to have enough bandwidth to pull it out of the box. For doing that, we have up to 4 PCIe card x16 and 2 OZP mezzanine throughout the unit, which allow us to have over 800 gigabit of data in and out. Just to complete the design, we made sure that the system was reliable and easy to maintain. With a few easy and tricks, we are able to allow to service one of the nodes without interrupting the function of the second one. The split cover allows us to access portion of the server. Replacing the fan, power supply change are all easy done and toolless. To summarize what the FB128AG offers: unbeatable performance with E1S drive support and outstanding capacity thanks to the NGD 12TB drives. A way to really utilize the data providing all network connectivity requires. In total, a dense system capable of replacing few servers in a one new rack space. Building the right information architecture is crucial to AI success. Data capture and distribution can make or break the AI or machine learning project. Besides the obvious AI and machine learning, the FB128 can be used in a variety of vertical markets, such as content delivery, oil and gas, virtualization, and automation. Those are all vertical markets. They have something in common. They generate a huge amount of data in a very short period of time. The FB128AG is a system that was built from the ground up to help reduce the effect of on the new data infrastructure, and it's ready for any workload. Thank you for your time, and if you have any question about AIC storage server, I'll be glad to answer during our Q&A session. Thank you.
One of the really great things about the AMD 7002 series processors is the architecture advances that we've made, and one of those is with PCIe Gen 4. And this allows you to double your PCIe bandwidth for your most demanding applications across HPC and enterprise. And one of those things with PCIe Gen 4 is our valued partners that have developed PCIe Gen 4 solutions. So first of all, with Mellanox, you are now able to get, with their ConnectX 6 solution, 200 gigabits per second of InfiniBand, which allows for extreme scale HPC connectivity. With Xilinx and FPGAs, you now have the ability to eliminate the bottlenecks that you've traditionally seen with acceleration solutions. With Samsung and PCIe Gen 4 solutions, you now have lightning fast data transfer, eliminating the bottlenecks that we've typically seen in the past with PCIe Gen 3 data solutions. And with Broadcom's new 200 gig Thor solution, you've eliminated the network bottlenecks that have traditionally been there in large enterprise environments. With PCIe Gen 4, which delivers 2 times the I/O bandwidth, you can now remove I/O bottlenecks from your environment and achieve incredible scaling.
Hello, this is Joe Kempler again, and now it's time for our Q&A section of the presentation. So we've had several questions come in, and the first one is for NGD Systems. And Scott, why is it important to have computational storage today, and has it existed before?
175 zettabytes of data in 2025 is what IDC predicted last year. They've changed that to over 200 zettabytes for 2025 this year. So the amount of data we're generating is huge, and the need to be able to collect that data is important, but the need to not move all of that data is very important. Kind of back to that idea that I can store it to the cloud all I want, but I get taxed heavily when I want to move it out. There's lots of solutions that exist to keep that traditional move of data one way or the other. But what we really need to look at is how to ingest that data, do something more valuable with it locally, and then send that result back out. And that also adds to the cybersecurity piece that we've been fighting with recently, and the fact that we need to be able to deal with data coming in and only useful information coming out so that that raw data doesn't become a security risk.
Scott, that actually feeds right into the next question that came in. How are the passwords or password managed across all the devices?
So for our particular solutions, if we're enabling a security environment using TCG, Opal, other things like that, the master key can be used across each of the individual devices for an admin key. And then we have the ability to do authentication keys in each and every one of the devices. And that device, because it's an OS talking to an OS, you can transfer that key through that secure path. And you can do decrypt and re-encrypt of data locally to each device. And we do the authentication keys based on serial numbers of the individual devices and not of the drive itself, so it's not a human readable number on the drive, but by way of the ASIC that we design has a unique serial number that we use for authentication keys to keep it super secure.
Thank you, Scott. With a savings of power, Federico, this one looks like it's for you. What did you do to verify the thermal design of the server?
So those NGD drive are really great. We don't really want to have the drive throttling down and reduce performance if the drive overheats. When we start designing the chassis, generally we keep in mind the thermal. So having the right fan, having the right cooling for starting from the drive in the front, which they get the cooling directly from outside, of course, down to the other in cards. So first, what we do is we do simulation. We start working with all the maximum configuration that the system can support, and then we'll drill it down. Once we have some samples, we populate those samples with the highest configuration possible, and we run it through various thermal scans. So we need to make sure that all the systems are in perfect balance. Noise and of course airflow throughout the system.
Thank you, Federico. The next one is for AMD. It's a long power too for Madhu. It says, why does AMD have a lower power value than the competitors?
Oh, it's an efficient design. That's an easy question. So we have a wide portfolio of SKUs, and for especially ROM, which is our EPIC 7002 class of devices, we have options all the way from 8-core to 64-core with the same footprint. And the TDP, we have a wide choice there, 85 watts all the way to 280 watts.
Thank you, Madhu. You actually have two more that rolled in. I'm just going to hit you all at once. So I'll ask you one, then the other. So one is which AMD processors have a PCIe Gen 4 and how many lanes?
Oh, good question. So our 7000 EPIC 7002 class of devices and our next gen Milan, which are EPIC 7003 class of devices, all of them have PCIe Gen 4, and all the SKUs except for one has 128 lanes of PCIe Gen 4 per socket.
Thank you. And then the last one for AMD, what is the max core count of an AMD processor today?
Okay, excellent question. So both for Rome and Milan, the maximum number of processors we have is 64.
Thank you, Madhu. And then for Scott, is NGD Systems the only vendor in this space? And what is being done to make it a standard?
Absolutely. So NGD Systems is the only solution that exists today that has the ASIC design that can be implemented. So that's what allows us to partner up and do things like the EDSFF form factor, which is paramount to the conversation of today's discussion. There are other solutions out there that are currently based on an FPGA or an FPGA accelerator platform. If you want to find out more, you go to SNIA.org and look for computational storage, and you can see right now the running count is 46 organizations and over 200 members helping participate in the architectural definition. And there's 3 other actual viable purchasable products from other vendors in the space. Again, all in that 2.5-inch U.2 or AIC form factor. So for the purposes of this conversation and this particular platform, we are currently the only solution available, with others coming soon from other vendors.
Thank you, Scott. Staying on the subject of form factors, Federico, this one looks like it's for you. Can I use any E1.S thickness?
All right, yeah, that's a great question because at the moment there is a variety of device coming into the market with different. So the connector is always the same. The interface to the compute is all the same, but depending on what kind of thermal solution the vendor of E1S use, there are different thickness. In this particular platform, we prefer to use the bare board, the bare PCB. In the case, it's 5.9 millimeter. We can also support up to 8.1 millimeter, but anything above that, it will not fit into the system. We prefer to use those slimmer kinds because of we can achieve a lot better density. And also, we are pretty sure that as a thermal solution, we can support, we can cool down those drives pretty well.
Thank you, Federico. We must have a lot of technical people or hardware designers in here, because here's another one on form factors and configurations. This looks like it's for Federico. What is the OCP slot PCI Gen 4? It looks like he's looking for a definition.
No, actually, probably definition. I understand what they're trying to ask is, OCP is a form factor that is been around for quite some time, and generally those OCP 2.0 specifically on this platform, they are PCIe 3.0. So there is not really a short answer on this. So the lanes going to the connector on the OCP are PCIe Gen 4. However, right now, there are not many manufacturers. They make those cards in PCIe Gen 4. So the form factor 2.0 is a little bit forgotten by the manufacturer. But as I say, we support PCIe Gen 4 all the way across.
Thank you, Federico.
And I go ahead and jump in and just to echo that point. And one of the reasons we've picked AIC as a partner in this platform is the innovation that's able to get that Gen 4 with those orthogonal connectors to be able to drive the airflow appropriately is paramount to the solution. I mean, in our particular case, to his point, we've worked with you guys on the bare board. We have the symmetrical design, and/or you'll see a lot of things if you Google E1S or EDSFF with these massive fins on them that are 15 and 25 millimeters to allow for the cooling of the device. which are part of some of the standards moving forward. But if you look at the platform, if you have something with a fin like that, you're losing drive count every time you put a device in that doesn't fit into the thermal requirements of what this particular platform can offer. So it's a great example of how partnering with AIC from an NGD point of view is great, because we're able to fill every single socket and not have a thermal constraint, because those orthogonal connectors and the fact that you have Gen 4 already deployed allows us to work together more effectively.
Well, thank you, Federico and Scott. We're going to open the mics now. So we're going to have, if you guys have a question, go ahead and ask any of the panelists. Again, from AMD, you have Madhu Indurthuri. He's the head of the storage division. You have Federico Papanini. He's a product engineer for AIC. And you have Scott Shadley from NGD Systems. So we're opening the mic now. They should be open. Are there any questions, live questions for any of our panelists? Now's your chance.
This question is for NGD. I think customer has a little bit audio problem and didn't hear the answer. And so he wanted to hear the NGD's response on how are the passwords or password managed across all devices. Can you repeat that response, Scott?
Yeah, sure. So I think that came from Philip Elder. So thank you for that. What we want to do from that perspective is highlight that we can use the master keys that come from a host implementation, and anything that's stored or used as a master key on the host can be transferred into the OS on each of the devices. So we can do a secure transfer of that password, or we can use authentication keys per device based on the master key. So the master key has, the ghost key type of thing, and then each of our devices will be able to manage that password using an embedded serial number of the ASIC itself, which is not human readable or available to anyone except for the device itself, to make sure everything's properly secure. And it can be scaled across all the devices in the system. So we can keep it a single master to all 36, or one master and then individual keys for each of the 36 devices. So each device could independently encrypt and decrypt its own information without having that master have to be involved.
Thank you, Scott. Again, all mics should be open, or if you'd like to type into the chat box, the question box, please go ahead and we'll read out your question for everybody. There's everybody has questions, so go ahead and ask away. Okay, is NGD Systems public? I don't know, you could probably, I don't think so, but Scott?
So right now we are a privately owned company. We've been through 3 rounds of venture and corporate investments, and having a very positive growth rate right now with deployed systems in the marketplace. So we've deployed product with autonomous vehicle manufacturers, data center partners, and including now a recent agreement to put product into space with the US Space Force. So not public yet, but if you want to participate in an IPO, we'll happily support that.
All right, Scott, I got another one that came in for you. Will the master key be unique to each system?
I replied in the chat as well. The master key can be based how the user wants that to be. So we can make it unique per platform, as in keep it on the AMD and the host OS, or it can be triggered into each of the devices if you choose to do so. There's multiple ways to do that. And we are partnering with several cybersecurity firms on encryption support and implementation to be able to provide those opportunities to the user. So it really comes down to how secure do you want it. If you want each device secure, you can create independent master keys. If you want to use a single master key, we can create a backup key on each device, or a single master key unlocks everything at once. So the encryption options are quite plentiful, to be quite honest, in this particular architecture, because it's an OS talking to an OS.
Thank you very much, Scott. Are there any other questions coming in? Last chance to go ahead and ask your questions. You should have a live mic, or you can type them into the question box. You have some very high-powered people here, so go ahead and ask your questions now. Okay, there's no more questions. So I'd like to thank you very much for joining the presentation today. AIC, AMD, and NGD Systems, thank you very much. So please rate this event. We value your feedback. We will post the presentations to www.aicipc.com. You can also download any of the presentations before you go from the handout section. Please follow all the AIC, AMD, and NGD systems on YouTube, LinkedIn, and Facebook. And in future webinars on February 3rd, we'll have transformed static architecture into dynamic data center in a few clicks. And on February 24th, we'll have maximize performance and minimize rack space and TCO. So again, we'd like to thank you very much for attending our webinar, and everybody make it a great day.
We appreciate everyone's participation. Thanks again for taking the time out.